Okay, good morning, everybody. What did you all learn from the experience of writing assembly language programs? Yes.
There are certain naming conventions that I kind of use, like keyboard.
Okay.
And I kind of used them incorrectly, and I kept on writing multiple versions of my program. And when I kept running it, it kept on failing. So I just couldn't get it on time until I ended up figuring it out.
Okay. So what was it that what was kind of the insight that you got that got you over the finish line?
More research.
Okay.
Do the project, and then that's pretty much it.
By research, you mean really studying the chapter in the book?
Yeah.
So part of what V is referring to is that there are some subtleties in how the assembler handles labels. In particular, there are a number of predefined labels. So for instance, KBD is always 24576. Now you don't need to know that because it's just KBD. And you can read the keyboard from there. And similarly, screen is 16384. There are some others. R0 through R15 is actually location 0 to 15 in RAM. The reason for this, we're going to explore it in more detail later on, but the heart of the idea, the core of the idea, is that these represent memory locations that are earmarked for some specific purposes later on. And initially, you can just think of them as resource places, places where you can put stuff or what have you. So that's those. And then there are some others as well, but those are the ones that you would have encountered in this assignment because you needed the screen and the keyboard to implement the fill assignment. And then for the multiplication assignment, it was telling you your factors are in R0 and R1 and your product is in R2. So so that's kind of the deal with those. Now, once you've got those, there were then two other kinds of labels. There were the labels in parentheses that corresponded to some line of code in your own program. And then there were just arbitrary labels and values starting at location 16, just as you created them. So something that's interesting about the way that the assembler works is the fact that it doesn't particularly object if you have a name that you just kind of make up and use. It'll give it a meaning for you. It's not really enforcing very much. So good, some good insights there. What else did anybody learn from the experience of writing an assembly language program? Yes?
I think it turned out to be a little hard to debug. I wrote a program, but I had it correct, and I spent like 4 hours trying to fix a mistake. That when I fixed it, it just ran. I was a little bit mad. Yeah, the fill one, I think I had the logic correct, but somewhere on a jump, I forgot to make a statement. It's a 0 or jump, or D and JA or JNE. I forgot to put a statement there, and it was wrong all the time.
So what made it especially hard to debug?
Code just seemed to make sense. I would read it over and over again. I'm like, this looks right. This looks right. Yeah, and then for some reason I had that weird bug.
Yeah, Andre.
Like it wouldn't really tell you when you would go out of bounds or like really far from where you thought you'd be. So like you could get to 24577, which is not even
right
actual address.
And it'll just happily keep on chugging. Yep. Yeah, that's true. And it's interesting to think about. If you have an illegal address, what should a CPU do? What this one does is it blandly ignores it. Is that right? What do you all think? What could a CPU meaningfully do?
Maybe throw an illegal bound exception of some sort.
Okay, but what does that even mean?
Okay, maybe it should put it and stop there. It's like, this is not good. This is not good. Something like that, just to kind of alert you. I don't know.
So, well, I mean, you've got some interesting ideas here, but I want to tease out their consequences. What would it mean for the CPU to signal an alert? What would that even look like on the circuit level? Yeah.
Maybe bits might be stuck instead of going, like electricity. I don't know. Someone that's getting it.
Yeah. What would it look like for the CPU to give you some kind of error notification? It can't just stop the program, because if it stops the program, it just isn't doing anything, right? We're on the bare metal. We have no support staff. What could it do? Just using your imaginations. But yeah, you're right. Debugging assembly code absolutely stinks. It's one reason people don't like to write it. So this is one of those moments where, it's said in life, you get a luxury, and once you get used to that luxury, it becomes a necessity, right? So we have a lot of luxuries in high-level languages, and we're so accustomed to them that they've become for us necessities. For example, memory protection. That's huge. We're so accustomed to, if we have a memory access violation, the computer starts yelling and screaming at us. And it does so rightly, right? If you've got a memory access problem, you ought to know that, you ought to be informed of that, and you ought to have an opportunity to deal constructively with it. There's nothing wrong with that, okay? But at some point, you actually have to implement those abstractions. And so that's where we are. They don't come out of nowhere. It's not like there's some magic computer fairy that just knows when you've violated a memory boundary. Ultimately, this is implemented in software as part of an operating system or a programming language implementation. And we're going to explore that later in the course. But painful though it was, a lot of what this project did was provide a valuable lesson. These luxuries that we've come to count on actually have to be created at some point. So, food for thought. But those are great observations. Any other lessons learned from writing an assembly language program? You needed to step away from the computer more than usual. So what you're saying is you just needed time away from it to let your brain organize its thoughts and figure out what the hell was going on, pretty much. Yeah. It's a good insight. And I think that's a good lesson in almost any programming situation. Sometimes you just need to walk away. And the reason for that being, there are times where our subconsciousness is able to make progress on a puzzle when our conscious mind is tired. Many times, actually, I've had the experience of having some insoluble problem where, just stopping and going to sleep somehow improves the situation. In the morning, things are clearer. Other times, taking a shower or something, and suddenly an idea comes about, or going and exercising, hitting the swimming pool or something. And yeah, sometimes you just need to let your mind work for you, and this is one reason why, sort of doing everything the night before can sometimes be a disaster, because you don't give your subconscious mind sufficient opportunity to help you process what you're doing and what's going on. Good. Any other lessons learned from assembly language programming? Other things you missed from a high-level language? Yes.
I like to think in terms of functions. Every time I'm programming,
Mm-hmm.
I'm like, let's say I wanna, apply like 10 numbers. I don't know, something like, I try to find the basic double operation, abstract it in a bigger function, abstract it, and then kind of work them through inside until I got it right.
Mm-hmm.
With like the first project of like multiplying, because I couldn't use functions, I'm like, how am I gonna do this? How am I gonna do this? Just think of the whole thing in one functions, it seemed rather painful. Like it seemed kind of difficult compared to how I was accustomed to doing it like in 150, where I can say,
Yeah.
It's a little function that adds two numbers, function that iterates through numbers and adding something like that. Yeah, so that was
So that's a pretty profound insight. Functions had to be invented pretty quickly in the history of computing because a big flat program is just too difficult for the human mind to deal with. What we seek to do with functions is break down a program into pieces where we can think about everything that's happening in the bandwidth of our short-term memory. So our short-term memory can track about 7 distinct items. That's why in an era before you all, phone numbers used to be 7 digits. That is, if I was making a phone call, I was probably making it within my same area code, and I could just do 7-digit dialing, and it made it easy to memorize a phone number. But when I was a kid, especially in the 70s, the entire state of Florida had 3 area codes. So in general, if you were going to go outside the area code, you knew pretty well what you were doing. And within, it was 7-digit dialing. Why 7 digits? That's what the short-term memory can store. Now we're all essentially at 10-digit dialing, and so we ask our phones to remember the phone numbers for us. It doesn't seem like much, but it actually overwhelms the short-term memory. And so when we're designing software, we need to figure out what do we need to do to keep what we're working on within our short-term memory. And that involves building functions that have intuitive names that clearly describe what they do. So it can be like one unit of thought to use that function. And then we've got lots and lots and lots of levels of function, so that at each stage we're just breaking it down into roughly 7 pieces. And it's kind of hard to do that because you have to do some creative thought to come up with what's the purpose of this function? What's its name? What's its job, right? But once you do that, the code becomes really clear. And yeah, in this particular machine language, this is impossible, literally impossible. So in chapter 8 of this book, we're going to create the infrastructure for functions. I think you'll be deeply satisfied. Yeah. Good. So this is a very elementary machine language, and you'll appreciate that in this next project when you create the CPU that implements it. Commercial grade CPUs often have much more sophisticated machine languages. They even some of them will even have provisions for really primitive functions, like a jump that automatically pushes the return address onto a stack for you that's maintained at the CPU level. I may give an example of one of those on Thursday, depending on where we get today. So what you all were working with seems like it's as bare bones as it gets, except that it's not, and I'm going to talk to you about that next. What do I mean? So in the history of computing, there was an important theoretical innovation that kind of paved the way for understanding what a computer is and what it can do. And so specifically this arose, whoops, get back here. This arose in the year 1936 with Alan Turing's PhD thesis. So specifically, what he was doing, this was a PhD thesis in mathematics. And he was trying to understand a deeper problem about how is it possible to build a proof or construct a proof, okay? And he reasoned about it in terms of imagining an abstract computing machine. And he showed that that abstract machine was equivalent in power to something that could build a proof arbitrarily. And this connection between computing and proofs is the central theme of Dr. Yorgi's functional programming class, which I know some of you are taking. And that unity goes all the way back to 1936, really, and the invention of the abstract idea of a digital computer. So this abstract idea of a digital computer is known to this day as a Turing machine. And you don't want to program with one. So what is it? What does it look like? How does it work? Remember, this is just a mathematical abstraction. Nobody deliberately builds one. But an electronic digital computer has no more power than this thing I'm about to walk through with you. Okay? So what are the components of a Turing machine? It has a tape, and this tape is infinite in size. So already we're getting more powerful than an actual physical computer, since none of our computers have infinite memory, which is frustrating. But anyway, so it's infinite, and you can move it left and right. So you've got this infinite stream of tape that you can move to the left or to the right. Now, hovering above that tape is a read-write head. So what's the concept of this read-write head? Essentially, it can mark a cell on the tape, or it can erase the cell on the tape. So this thing just kind of moves back and forth. It makes ink blots, or it can erase an ink blot. And that's it. And then it's got some notion of instructions. You know, the instructions saying, being based on check tape, and then, you know, do one thing if marked, and do another thing if empty. So that's it. And so the claim is that anything we do with an electronic digital computer can be modeled with this thing. And I imagine at this point, at least some of you are scratching your heads. How? For full details on Turing machines, you can take the Theory of Computation class. But for now, you can imagine it like this. By marking cells on the tape or erasing them, you have ones and zeros. By reading the cells, you have if statements. Furthermore, the if statement, when it's deciding what to do, is performing a jump. So, if it effectively has a 1-bit data bus, which it does, right? Erases, reads, blots, and so forth. Even given a 1-bit data bus, you can build a full-blown computer. It's just that a 1-bit data bus is actually even more painful to program than an assembly language with a 16-bit data bus. But once you have a 1-bit data bus, there's a sense in which you have everything you need. Everything you need to write astonishingly long programs to do simple things. But there it is, right? So, this idea of a Turing machine is really, really important when thinking about the capabilities of a programming language. That is, if a programming language is capable of simulating a Turing machine, we say that that programming language is Turing complete. You know, if you can simulate a Turing machine using a programming language, we say it's Turing complete. So every programming language you've studied thus far is going to qualify as Turing complete. You can simulate a Turing machine in Python, in Java, in Haskell, what have you. Okay? You can even simulate one in Hack assembly language. You know, it's not pretty, but you can do it. So, the reason I went over this with you all is to give us a way of thinking about what would a really, really simple CPU look like. So here's what I've got in mind. We're going to imagine a CPU for a Turing machine. Now, this CPU for this Turing machine is not exactly going to, how shall I put this, have a fully infinite tape going on. We're going to have a finite memory, as we've been doing. So here's kind of what I have in mind. Let's imagine that in this CPU, we have just 6 instructions, okay? So the 6 instructions are, we'll call it ML for move left. We'll have MR for move right. So that's moving the tape 1 spot left to right. Let's have WR for writing the tape. Let's have ER for erasing the tape. And then we'll have JC for jump clear and JS for jump set. So that gives us 6 total instructions. 6 total instructions. How many bits do I need to create a machine language for these instructions? If I've got 6 instructions, how many bits do I need? 3? Why 3?
Because it's 6 is greater than 4, which is 2 bits. 8 bits would encompass the 6.
Exactly. So if I've got 3 bits, that gives me 8 distinct numerical values, which is 2 more than the number of instructions that I have. With only 2 bits, I would only have 4 distinct values, which is 2 fewer than the number of instructions I have. Yes.
You can explain why you thought about it that way? Because that sounds insightful, but I kind of don't think you can come up with that idea.
Okay, so I have 6 distinct instructions. As we talked about in chapter 4, each instruction needs a unique pattern of bits to identify it. And that pattern of bits, of course, is what's ultimately going to be processed by the circuit that is your CPU. Right? So I need 6 distinct bit patterns. Obviously, I could achieve this with 6 bits, right? I could have a 1 for each instruction in a specific position. But that means my programs would require more memory to store them. So what I want to do is use the fewest number of bits I can to represent an instruction. So if I have 3 bits, that means I can have separate 3-bit patterns for each instruction that are unambiguous. And so that's what we're going to do. Yeah. So let's imagine what that might look like. Okay. So to think about this, one thing that I think I'm going to do is consider the instructions that have something in common ought to have certain bits in common. Like, I'd like to have a bit to tell me if I'm jumping or if I'm marking or unmarking the tape or if I'm moving the tape. So here is a scheme that I came up with. So we'll have bit 2, bit 1, and bit 0. And so in my scheme, I'm going to say if I'm moving the head at all, there's going to be a 1 in that position. And if I'm not moving it, it'll be a 0 in that position. Then I'll say if I'm jumping, I'll have a 1 in this position. And if I'm not jumping, I'll have 0s in that position. And then I'll notice that every instruction is in pairs. And so I'll use this lowest order bit to determine which instruction in the pair I'm using. So if I'm going to move left, that would be a 1 here. Moving right would be a 0. If I am writing, that would be a 1. Erasing will be a 0. Jump on a clear will be a 1. Jump on a set would be a 0. Okay? So the next thing I need to do is think about where am I going, right? What are my destinations going to look like? And so in thinking about that, I need to decide how am I going to represent that within an instruction, and what does that mean for how big a program I can have? Okay, so the way that our book's architecture solves this is that idea of an A instruction, right? Where you've got a 0 in the left if it's an address, and a 1 on the left if it's a if it's doing a calculation, right? So we could do the same kind of thing if we were so inclined. So at that point, it's just a matter of deciding what's the total width of the instruction bus, and that -1 is the number of bits we have available for our program space. So let's just make something up. How big a program do you all think we should be able to have? Eight instructions, 16, 32, 64, 128. We all know it's a power of 2. Yeah.
When you say how big a program,
Mm-hmm.
do you mean what is the length of a string that contains all the instructions we need to run that program?
It's actually just the number of instructions total in the program.
What is an instruction?
values. So how many of these do we want to have available in a program?
I mean, a basic one would be something like just move right, put 0 there, and then move left, something like that.
Right. So that would take 3 instructions. But whenever you're designing a CPU, you have to decide what's the maximum length of a program. Because that determines the number of bits you store in the program counter and the number of bits that you're employing in the address setting instruction. So how about, just to keep it super simple, let's go with a maximum of 32 instructions in a program. This is obviously not a practical computer, right? But the difference between this and a practical computer is just more instructions. Okay, so with 32 instructions, we need a 5-bit program counter. And so what we could do would be to say, we also then have a 6-bit instruction bus. So we can do an A instruction as 0, 1, 2, 3, 4, 5. And then the C instructions will just be these guys, but we'll just fill in some ones. So we'll say 1, 1, 1, and then blank, blank, blank for the values coming in from that table right there. Okay? And so, you know, by coincidence, this winds up looking an awful lot like what you're going to be working on, right? So, time to build a CPU. Oh, we need one other thing, right? So we're going to need, again, a program counter, 5 bits. We're going to need an address register for our jump targets. And then we're going to need a head register to track where we are with the motion of the read-write head. And so this means we now need to decide how big RAM is going to be. And just to keep things uniform, we'll just say it's 5 bits. So the size of our tape is actually 32 elements. So you really don't want to program with this. But again, the distinction between this and a real computer is simply size. Okay, there isn't anything else that makes this distinct. So let's think about what this is going to look like as a circuit. Okay? So thinking of this as a circuit, we're going to envision, much like the computer we're building, that there is this ROM, this read-only memory that contains your program. Okay? And this ROM has an input that lets you pick which instruction am I going to, right? And then it has an output that actually gives me that instruction. So when I think about my CPU, it's got the actual instruction bits coming in there, and then it's got this output, which is basically the output of the program counter, telling the ROM which instruction to give me next. Now, internally, we're not all that concerned about how the ROM itself is organized, but the heart of it is what you did in chapter 3, right? Except that you can't write to it, so it doesn't have any demultiplexers for setting those load bits. Instead, it just, the instruction address comes in, it uses a multiplexer to select from all of the instructions in its memory which one is being output, and bam, out it goes. That's all this is. And then the instructions themselves have been burned onto the silicon. That's what makes it read-only. Okay, so an instruction comes in to the CPU. So let's think about what gets affected by it. So looking back at the table of instructions, what really distinguishes an instruction is very simple. What changes as a result of this instruction? So let's start, and then we've got our registers over here, and of course there's going to be main memory, the RAM, or the tape, if you prefer. So, the first decision, of course, is whether it's an A register or a C or an A instruction or a C instruction. So let's think about the A instructions. What changes in the computer if I set an A instruction? Right, the address register. That's it. So let's think about what that looks like on the circuit level. Okay? So if I am going to change the address register, I need to have the load bit as a 1 on that register, right? So trying to figure out the best way to sketch out what the circuit looks like. Let's just do this. We're just going to look at the circuit in pieces, and we'll talk through how those pieces get integrated together, okay? So the first big decision to make, right, is I've got this instruction coming in, and what I need to do is I need to isolate the highest order bit. In other words, bit 5. So I have instruction 5, and one thing this is going to do is it's going to go to the load input on my A register. But it can't go directly because I only load the A register on a 0. So if it can't go directly, what do I need between that bit and my A register? For this one, it's not even that complicated.
Repeat the question.
What logic gate do I need between my instruction and the load bit on the A register? So my higher order instruction bit, if it's a 0, I want the A register loaded. The A register is looking for a 1 to load. So I just need something very, very simple. And that's too complicated. I need something very, very, very simple. A NOT. Right? So that high order bit is coming in through a NOT gate. And by knotting that high order bit and wiring that to the load, I allow a write to happen to the A register. And then on the input pin for the A register, we have bits 0 to 4 of my instruction. So part of what's happening in the CPU is that you set it up assuming that every possible write is trying to happen at the same time. Whether or not it happens depends on the load bits that get assigned to the various things that can change. And that's really at the heart of instruction decoding. You have to figure out what's going to change, figure out when it happens, and then you basically set up the circuit assuming everything's changing, but you only allow the changes when those load bits are set according to what you've got in your machine instruction bits. That was a mouthful. Did that make sense? Not really? Okay. We're going to keep working on this, and hopefully you'll see where we're going. But again, the basic idea is all a machine instruction ever does is change something. And when we set up the CPU, we always try to change everything that can change, but we only allow a few of those changes. So here, those instruction bits are constantly trying to be loaded into the A register, but we only allow it when this is a 0. It's like these bits are knocking on the door of the A register. Please, please let me in. But we only let it in when we've got a 0 in the upper bit. It's pounding at the door. Please let me change. Yes?
If we think in terms of how we've been assembling assembly code, the 2 binary code, and seeing like the program going line by line, execute, is this sort of the same thing? Does it like take one line of string, take into that black box, change something about it, and return the output? Or it's the whole instructions? It's like the whole list of instructions.
It's one instruction at a time, which is really important, right? The CPU only ever processes one instruction. So it's constantly fetching the instruction that corresponds to the value in the program counter.
Oh, that's like one line at a time.
Yeah.
And then why did we choose instruction 5 as a determinant for load bit? What's special about instruction 5?
Well, it's this. It means that the binary value of the instruction taken as a whole is the address. It's just conceptually very straightforward. It's also completely arbitrary. I could have stuck that 0 at bit 2 if I felt like it. Why? Because I'm designing the CPU. I can do whatever I want. But it's pretty intuitive to have it at the leftmost bit because the rest of these bits just is the address. Yeah. So for example, when I'm writing my assembler, which is next week's project, when I see the @ sign and an address, I can take the address, convert it directly to binary, stick a 0 on the left, and now I've got my instruction. If I wanted it to be bit 2, I could convert it to binary, then kind of split it in the middle, stick a 0 in there. It's actually kind of obnoxious, right? From the standpoint of being humanly understandable. Now, machine language is not terribly humanly understandable, but we don't want to introduce unnecessary obstacles to that. And so that's part of thinking about this. All right. So that's A instructions right there. So next, let's look at moving the read-write head. Okay. So when we're moving the read-write head, it means that bit 2 on the instruction is a 1. So I've got some register, which is the head, and it has an input, right? And then it's got this load. So when do I actually get to do the load? Let's think about it. Remember, you just got these 6 instruction bits, and from these 6 bits, you decide whether or not to do a load. Bit 2 is for this instruction. Is for any head moving instruction. Would it be enough for me to wire instruction 2 to this load bit? Or would I need any additional logic? Yeah.
Why did you choose bit 2? What's special about bit 2?
I made it up.
So even bit 3 can work for bit 4.
If I decide to do it. Remember, all machine languages are designed by humans, and humans have to pick which bits have which meanings. And the only reason those bits get those meanings is because we set up the CPU to behave in the way that corresponds to that.
But every implementation you make has to have a different bit to correspond it to. For example, like writing or tail or move left, they need to go to a bit that is neither 5 nor 2. Is that correct?
Because we want to keep things as clear as possible.
Okay.
So my question for y'all though is this: would it be enough for me to wire instruction 2 to the load? Yeah, Andre. It moves the tape. We're moving the tape left and right. So you can think of it as move the tape left to right or move the head along the tape. The tradition is to think of the tape moving. I think it's a little easier to think of the head moving because that corresponds to picking which address and RAM it's affecting. But those are equivalent ideas. So the head register is saying, this is the position on the tape that gets ink blotted or erased or checked. So I've got this instruction, this C instruction, move left or move right. If I'm moving at all, bit 2 is a 1. Otherwise, it's a 0. The question is it enough for me to wire bit 2 to the input register, to the input pin on the head register, or is there anything else I need to do? Yeah, Andrew.
Are you like asking if it's enough for us to know like which direction we're moving?
Oh, we haven't even worked on direction yet. We're just deciding, does it change or does it not change? Direction is next. And that'll be about what the input is to the register. Yeah.
To decide if we write or erase first?
Not really, because this is just moving. Oops. There we go. This is just moving the head. So writing and erasing is a different instruction. Yes.
I think it's enough then. Because if the only thing about is like on bit 2 having a 1,
Mm-hmm.
I mean, that's it.
Okay. So that's a bold proposal. Let me posit a situation and tell me how we might deal with the situation. So let's say we have a situation where we have an address instruction and bit 2 has to be a 1 to represent that address. At that point, the address register gets that full value in, but at the same time, we're also going to change the position of the head. If I give an address instruction like say 0, 0, 1, 1, 0, bit 2 is a 1. Because this is a 0, out here we get a 1, and we get a load into the address register. But at the same time, because this is a 1, we're now getting a load into the head register. And I'm suggesting that is undesirable.
I have a question.
Please.
Then I probably kind of didn't understand exactly what we're doing. So these instructions happen at the same time, like, because I think in terms of like one happening and then counter going and the other happening.
One instruction happens at a time, yes.
Then
But the bits from that instruction are connected to everywhere in the CPU where they could matter.
we don't need to have a situation where we can load into an A register and still move ahead. Like that should never happen.
That should never happen,
Okay.
right? Because at that point, the machine becomes unprogrammable. Every time you set the address register, if there's a 50-50 shot that you're moving the head, you're going to lose your mind, right? Yeah, V. So what would a NOT gate do for us? No pun intended, right? Sorry, that was terrible. Terrible. Yes.
What if when you go to load into a register, we flip the second bit to be something that is not 1, so we can use it, and after that we flip it back to move ahead.
Thing is, everything's happening at one clock instance. Yeah. We can't, all sequencing happens as we go from one instruction to another. just with our 6 instruction bits that we're getting right now, we have to decode this. Okay? Let's look back at the bit pattern for an instruction. Yeah, Andrew.
So just like look at the bit at the same time, you can just like see if they're both one, then you know that's not an address.
Exactly. And how do we do that? What logic gate would we use? An AND gate. So check it out. Oops, I wanted to erase. There we go. I'm going to put an AND gate here, okay? And I'm going to have instruction 5 be wired to one of the inputs of the AND gate, and instruction 2 wired to the other bit. So if they're both 1s, we get a load. But if we've got an A instruction happening such that there's a 0 hanging out here, a 0 comes in, suppresses this bit, and keeps us from doing the load. Makes sense so far? Okay. So the next thing we have to think about is the input, right? So in effect, what we need to do is we notice we've got this output here. And then that output needs to be routed to 2 different circuits, +1 and -1. Okay, so you have it output. Let's say moving left is -1 and moving right is +1. In the end, it doesn't really matter, right? It's pretty arbitrary. That's one thing I'm hoping you all start to appreciate is everything about a CPU is arbitrary. It's just stuff we make up. But we want to think about it in terms of how programmable does it make the circuit, and how easy to implement does it make the circuit, right? So I've got a +1 and I've got a -1. I somehow need to pick between these 2 in some mysterious way. So let's put a little mystery box here. Let's have both of these guys go into the mystery box. And then the output of the mystery box is the input. So this mystery box has to pick between these 2. What kind of circuit do you all think the mystery box might be? What's that? A multiplexer. Okay. So what's going to be the select bit for the multiplexer? The 0 bit. Let's come back over here. We have move left and move right. The only thing distinguishing them is the 0 bit. Now, is that 0 bit, if I wire that 0 bit directly, uh-oh, my battery is running low. How long do I have? I have 6%. Okay, but how long is that? I need time. Okay. I have 9 minutes. Think about this while I grab my charger. I'll be right back. All right, little nice morning exercise. Never killed anybody. All right, let's plug this in. It's happy now. Power plugged in. Whew, okay. Instruction 0 is going to be wired to the select bit. Question I was posing is it enough? Yes.
Again, we need to be careful so that if in instruction 0 you have the 1, instruction 2 you have the 1, and instruction 5 you have the 1, they're not going to conflict. Is that the case?
So let's think it through. Let's imagine I have an A instruction that has a 1 at 0. So that picks between these. Here's the question. When that pick comes here, is there a problem if the bit 5 is a 0? Okay, why is it a problem? It's actually not a problem. And the reason it's not a problem is that we're already using bit 5 to mask the load bit. So it doesn't really matter what this multiplexer spits out if we can't do the load.
As a result of the load.
Right. So this is an example of some of the subtleties that happen when designing a CPU. Sometimes you care, and sometimes you don't. And the difference between them is this. Are you making a decision about what gets written, whether something gets written? We can actually make instruction 0 the select bit on this multiplexer without any worries at all, because all it's doing is deciding, is the +1 or -1 value knocking to get into the register? It's not deciding, does the value get in? Big difference. Very big difference, right? So at this point, we've actually designed a circuit that handles A instructions and the first 2 instructions in our machine language. Notice it really wasn't that hard, but there were some conceptual obstacles we had to navigate. But don't worry, we're going to keep going. One thing I do want to point out is how not arbitrary my bit assignment was here. You know, I said initially, right, they're both moves, so let's kind of mark that with a 1 and not moving with a 0. And on one level, that might have just seemed like an intuitive classification scheme, which it arguably was. But I had a deeper agenda there, which was to make it really, really simple to decide whether I was writing the head register by directly routing that bit into its load bit, mediated, of course, by that AND B. So, what does this imply? As you're designing your Project 5 CPU, I want you to assume that the designers of the machine language instructions picked the bits as they did to make it easier to create the circuit. In other words, every single bit both has a defined purpose, and that purpose is easily realized in terms of load bits and select bits. In fact, you've got a block of 6 bits that are just going to go straight into the ALU unmediated. Okay. Obviously, this CPU doesn't have an ALU because it doesn't actually do any arithmetic. You would have to actually write a program in this machine language to add. As we've seen, it's not terribly difficult to create an adding circuit, and it's much better to have that as a machine language instruction. But it's not strictly necessary computationally. But you really want it. You want an ALU, like a lot. it's actually an interesting trade-off. The more you cram into your machine language, the more complicated your CPU is, which leads to issues like cost, expense, and so forth. Okay, and importantly, cycle time. The more complicated the CPU is, the longer the propagation delay is for a clock cycle, and in a sense, the slower it'll run, right? But the more that's on the CPU, the less you have to do in software. But there's an awful lot of stuff that could be done either in hardware or in software. And deciding which of those to go with is fundamentally an engineering consideration. Yeah. Anyway, okay. So why don't we look at write and erase. So write and erase are concerned with whether we are performing a write to RAM. So here is RAM, and RAM is actually going to have a couple of inputs, right? One of those inputs is actually the output, and this is going to get tangled, so just forgive me, okay? The output of the head register is an input to RAM. Why? Because it's picking which bit in RAM is going to be read or written. It's picking which bit in RAM is going to be read or written. Now, in the CPUs you all design, there's no separate head register. It'll really just be the A register that tells, what you're doing to RAM. In this CPU, the A register is a little less busy. It's really just an instruction destination target. In the hack CPU, it's actually serving two different purposes. So that's one thing that comes into the RAM. The other thing coming into the RAM, well, there are two other things, sorry. The RAM, of course, is going to have a load bit, right? And then it's going to have a value bit. So to implement the writing and erase instructions, what we need to do is work out a circuit that takes the bits for those from the instruction, decides whether or not this load bit is a 1, and then decides what bit is actually coming in here. So let's look back at the instruction. Looking at bits 2 and 1, in what situations are we updating RAM? What combination of bits means a RAM update? Close. Very close. What would, when you said NAND, what were you imagining NANDing?
Yeah, it's non.
So you could do that. You could not bits 2 and 1 and then AND them. Or you could use a NOR gate. In other words, we want that load bit to be a 1 when both of these are 0. So with an OR, you get a 1 unless you've got 2 zeros. So with a NOR, you can put in 2 zeros and get a 1. If it's simpler, you can just think of it as, let's OR these 2 bits and then stick a NOT gate on the end. But Jack's right, we could equivalently NOT the inputs and then just AND them. So let's come back over here to the load. So the load, we're going to have instruction 2, instruction 1, and we're going to OR these, and then that's going to go into a NOT. Now, for the load bit, is that all we need, or do we need anything else? For the load bit for RAM, do we need anything else? anything else at all? Hint, you do. There's another little thing we need to do. It's kind of similar to when we were figuring out what we were doing with the load bit on the head register. Yes?
Make sure same thing with the bit instructions that we're not like reading the address.
That's right. Again, imagine we have an address instruction with zeros in those positions. Now we're suddenly corrupting RAM, which, while humorous potentially, is also frustrating. Okay. So yeah, we're going to need an AND gate. And so specifically, we're going to AND the result of that NOR with instruction 5. So one thing I'm hoping you all are seeing here is that these instruction bits are getting wired all over the place in the CPU. Those things are being sent everywhere, wherever they happen to be pertinent. All right, so the value bit, though, is super simple. Look back at the instruction. So we're looking at write and erase. The value bit. What's the value bit going to be? Exactly bit 0. Okay, now why is that the case? If we're going to do a write, we're going to mark it with a 1. If we do an erase, we're going to mark it with a 0. Again, the instruction set design is in part about making the circuit as simple as possible. So, whoa, wait a minute. Flying all over the place. Instruction 0 then is going to be our value bit. Bam, there it is. So at this point, we have actually created the entire CPU except for the jumps. And guess what? The jumps aren't going to be all that hard either. Okay. So we got to talk about the program counter. Okay. So when you designed the program counter, what inputs do you recall it having? So this was in chapter 3. It had like features. What were some of the features of the program counter? It had an increment feature. Good. And right, that was the increment, the add one. And then it had another feature as well. You all remember that it had a load bit and a 16-bit input? Right? So in other words, if we want to do a jump, what we can do is replace the program counter with the contents of the address register. If we don't want to do a jump, we set increment to be 1. So this winds up looking pretty interesting. And once we do this, we've got a CPU. Let's see if we can do it in 5 minutes. So program counter. Let me sketch that down here, say. Well, we're going to need RAM as well. So we have the program counter. It has an input, and that input is just going to be the output of the A register. If it's going to jump anywhere, it's going to jump to where the A register says to go. Okay? Then it's going to have, once again, a load bit, but then it's also got this increment bit. So effectively what's happening is we need a circuit to decide if we're jumping. And if we are, load is 1 and increment is 0. And if we're not, load is 0 and increment is 1. So we can actually work backward. We can posit this decision circuit and say if this decision circuit outputs a 0, then we increment. In other words, let's see. I need a NOT gate. If we're not jumping, it outputs a 0. So we NOT that to get a 1 on the incrementer. And if it outputs a 1, you get a 0 on the increment and a 1 on the load. So if we can figure out if we're jumping by emitting a 1, then we're all set. Okay? So ultimately, how do we decide if we're jumping? Well, looking at the instructions, was there a magic bit telling us that an instruction was a jump instruction? What bit was that? Yeah, it was bit 1 right here. So we know that instruction 1 plays a role. To avoid an address register problem, what other instruction bit plays a role? Bit 5, we know we've got to AND this with instruction 5, right? And then what we have to do is examine the condition, right? So let's look at that. Oh, you know what? I got my instructions backward, I think. Well, we'll see. Yeah, these are backward. This should really be JS and JC. Right, I think it's going to be a little clearer, make the circuit a little simpler. If I've got a 1 on instruction 0, then I'm looking to match a 1 coming out of RAM. If I've got a 0 on instruction 0, I'm looking to match a 0 coming out of RAM. So, what does that mean? I've got, in order to jump, instruction 1 has to be true. Instruction 5 has to be true. And now I have a choice. I could have instruction 0 and the output of RAM, since I've only got a 1-bit RAM, right? Or I can have not instruction 0 and not RAM. So I wind up needing to build a circuit that does this. And if it does this, it emits a 1 and it jumps. Otherwise, it emits a 0. And you know what? Once we've got that, we have a complete CPU. Again, this isn't a very good CPU. You would never, ever want to program it. You would never want to write a compiler for it. You wouldn't want to manufacture it. But all of the principles of building a CPU are in place. Right? And what are those principles? You can jump, you can change RAM, and you can change what address you're changing. Yeah, and that's enough. Obviously, your Project 5 CPU is more involved than this. But the principles are all here. The principles are all here. Any questions, quick questions before we wrap up? V. How do we study for the midterm? That's an excellent question. I'm going to distribute a practice exam ahead of the midterm. The midterm is next week or the week after, I forget.
I don't think it's next week.
Let's look. The midterm The midterm is on the 25th. So what I'm going to do a week from today, so on the 18th, is I will distribute a practice exam. I want you all to try to work the problems on the practice exam, bring it with you on Thursday the 20th. We'll go over the answers, then we'll have the midterm on the 25th. The midterm will cover chapters 1 through 6. So fundamentally, I want you to be able to do stuff like, if I give you a truth table, design a circuit. I want you to be able to give short answers that do things like describe how does memory work, how does a CPU work, that kind of thing. So I'll be assessing whether you've internalized the lessons I was aiming for you to gain from chapters 1 through 6. Yeah, great question. Okay. Oh, yeah, one other. Yeah.
Is there any way you can get us the practice system a little bit earlier?
Oh, yeah, if you really want to. Would it make you feel better? Okay. Maybe I'll post it sooner then. Maybe today. Just because you want it sooner. All right. Cool. Any other questions? All right. So I want to strongly encourage you to start your CPU before Thursday's class. Between now and when the CPU is due, and it's due Monday night of this coming week, we have Thursday's class. So of course, we got office hours, but if you start working on it today or tomorrow, bring questions with you to class on Thursday. My intent is to spend some amount of time on Thursday answering conceptual questions as they arise. My hope is that what we went over today at least gives you a framework for how you even think about starting this thing, which is very intimidating. But I want you to dive in and come to class Thursday with questions, and we'll talk about it. All right, have a great day. Oh, sure. What do you want to look at?
The last line, scroll up. Down. Yeah, the condition to make it easy.
Oh, yeah. There we go. Yeah. Sorry, what?
A lot of it is like instruction 5 or stuff and the table that you made with all the rules that and stuff.
You mean this?
Yeah. So I don't know how to really explain it. Like what was instruction 5 and like
Right.
4?
So this is instruction 5 right here. So you lead off with a 0, it means the remaining 5 bits are address bits. For non-address instructions, we fill in 3 ones here. Something you may have noticed, these 2 ones don't actually matter. They could have been 0s and it still works. And the same will be the case with this project. This is the money bit.
Okay. That makes a lot more sense.
Yeah, good question.
Thank you.
Sure.